Okay, now let's learn about seismology. Seismology is the field of science which studies the earthquake waves. And actually, seismology is a quite old field of science which dates back almost 2000 years to the Chinese. So here on the picture, on this right side, you see the first known seismograph. This is a very heavy metal instrument having eight frogs and eight dragons on it. And these dragons or frogs are showing eight major geographic directions. And there are tiny balls in the mouths of these dragons. When earthquake happens, the balls from the mouths of dragons will fall to the mouths of frogs. In this way, they could actually understand the direction of the earthquake. However, now we have a little more useful seismographs, which we use for recording the seismic waves. And we use these records of the waves to understand the location and the magnitude of the earthquakes happening. So let's just talk about a basic type of seismograph and understand its principle. So usually a seismograph actually is consisted of a drum with a piece of paper wrapped around it, a pen to draw the seismic waves, and also a foundation. So we usually have these seismographs attached to a foundation like a concrete block buried in the bedrock, like you see in this figure. That is really important because that actually helps us to get clean and reliable signal from the earth. And this seismograph mechanism attached to the bedrock via a concrete block is going to help us to record the seismic waves. Here we have this arm attached to the concrete block. And then we have this drum. It has its own tiny motor to make it rotating all the time, very slowly. And then we have this arm, actually pivoted from this joint in here. So when we have earthquake, when we have this ground being shaken by the earthquake waves, the pivot, the main rod in here and the drum are going to move with the earth itself. However, the arm is going to be moving freely. And with this free movement, we actually can draw the lines on this rotating drum, on this paper. And here you see an example of a record from a seismograph, which we called as seismograms, showing the waves drawn by this arm. So usually for having a good information about an earthquake, we need more than one type of seismograph. By using different orientations of the arm that I showed in the earlier slide, we can record both vertical and horizontal ground motion by seismographs. And we call these records we collected using seismographs as seismograms. Here you see an example seismogram with three groups of waves. You can actually distinguish them from their different looks. Red lines are showing 1 minute segments along the drum, along the paper wrapped on this drum. So the first group is going to be the P waves. And then there's the second group called S waves. And then we have this third group called surface waves. Now let's learn a little more detail about these different types of waves. So here let's talk about the types of seismic waves. First of all, we have two different types of seismic waves, body waves and surface waves. And when we talk about body waves, we talk about the waves traveling through the Earth's interior. And we have two different types of body waves based on their mode of travel. First, primary waves, or we call them as P waves. In this case, it's going to be compress and expand motion happening. Like you see in this spring or a toy, when you pull it and push it back, you see that there is a region of the spring is going to be compressed and released and moving along the distance of the spring. Here you see. So this movement direction is going to be called as wave direction. And then there'll be some expansion and compression going on along the wave direction. So this is a real good example showing how P waves actually move in the ground. There are two really important properties of the P waves that we need to keep in mind. First, they can travel through solids, liquids, and gases. This is important. And also, in generally, in any solid material, P waves are going to be travel faster, around 1.7 times faster than S waves. These are really two important properties because they actually help us to identify different waves and also identify the location and magnitude of the earthquakes. We will learn about this later. Now let's talk about the other type of body waves, secondary waves or S waves. So since you can get it from the name, they are secondary, so they come later. And in this case, we can have this example of a rope to understand how S waves move. So if we create this tiny wave shape by shaking the rope, this shape is going to move along the rope towards right, and this is going to be our wave direction. However, the shape of the rope is going to stay as it was, and we actually can say that the particle motion is going to be following this directionality of the shaken rope. Like this part, the particles are going to be moving towards upward, and this part, the particles are going to be moving towards downward. So again, the secondary waves or S waves will have several really important properties in comparison to P waves, which is again important for us to understand to identify the magnitude of the locations of the earthquakes. So this shaken motion at right angles to their direction of travel. And really important, S waves can travel only through solids. They'll be slower in velocity than P waves. However, they will have slightly greater amplitude than P waves. So just by, thinking about this information I gave you, you can say that the S waves are going to be more destructive compared to P waves because of the directionality of their particle motion, but also because of the greater amplitude that they have. And then there is a second type of seismic waves we call as surface waves. There are different types of surface waves, such as Rayleigh or Lowe waves. They travel along the outer part of the Earth. So as you can get it from their name, they'll be traveling on the surface of the Earth. They have a quite complex 3D motion, and they are the ones creating the greatest destruction because of their complex motion and greatest amplitude that they have. So these surface waves will have the greatest amplitude and slowest velocity compared to PNS waves. And they will have the greatest periods, which means that the greatest time interval between the crests of the waves. So by just, thinking about these, we can say that if we are recording with a seismograph, we will first record P waves, and then S waves, and then surface waves. So here let's look at this picture to understand how they actually going to be recorded on a seismograph. So let's say here we have the hypocenter of an earthquake. And then we have these three seismographs creating these three seismograms that you see in these pictures. First seismograph is going to be quite close to the hypocenter of the earthquake. And then the middle distance, we will have seismograph 2, and then the furthest away, we will have seismograph 3. For the first one, we know that P waves and S waves are going to be traveling more or less together, even though there's a difference between their velocities. For the short distances, that difference isn't going to be distinguishable or not as large. So here in the seismogram, you see that we have P waves and S waves, and the distance in between them isn't that big. And then we have surface waves coming quite late compared to P and S waves. So there's a distance between the S wave package and then surface waves. So if you go a little further away to seismograph number 2, this time we have a greater distance between P and S waves because now we are traveling along a further away distance, and the distance between P and S waves is more distinguishable. And then, of course, we have surface waves. But by looking at these recordings, you also can say that when we go further away, the amplitudes of these waves, P, S, and surface waves, are going to be smaller compared to the first seismogram. But if you compare the amplitudes of each group of waves in the same seismogram, you will see that the S waves are going to be larger, greater amplitude than the P waves, and the surface waves will have the greatest amplitude. And then if you go even further away, we may even be able to see only P waves because S waves are going to take way longer time to arrive, and we don't see them in this seismogram yet. They'll be somewhere after the seismogram, time limits that we can see. So by using this information from the seismographs, we can locate the source of the earthquakes. But first, let's start with learning the terms for this. We have focus or hypocenter, which we know it is the place within Earth where the earthquake waves originate. So it was on the fault surface. And then right above that hypocenter, we have epicenter on the surface, directly above that point. And then we have epicenter. Actually, we can locate using the difference in velocities of P and S waves. Now let's remember that picture I showed you before with 3 different seismographs and the shapes of these 3 different seismograms. We know that there's distance between P and S waves increasing by the distance of the seismograph, the instrument, to the hypocenter or epicenter of the earthquake happening. So, for locating the source of an earthquake, we definitely need at least 3 stations and the recordings from these 3 stations. And what we do, for each station, we determine the time interval between the arrivals of P and S waves, and then create this travel time graph. Depending on the distance in kilometers, this distance actually is the distance of the instrument, the seismograph, to the earthquake, and then the time. And after creating this graph, we can use it to determine each station's distance to the epicenter of the earthquake. Once we have those distances, we use the location of the seismograph, here Nagpur, Darwin, and Paris, and the distance to the epicenter, and identify the location of the earthquake by drawing circles around these seismographs. So when we have this point where all 3 circles intersect, we call this point as the epicenter of the earthquake.